Hi everyone, so welcome to this third lecture on the topic Dynamical Systems, Networks and Applications. So today is a special lecture because it's more a modeling lecture, although there will be some math at the end. Okay, so we will talk about mathematical modeling of emotions, and I will deal in fact with the functional aspect, not the physical aspect. So today we will not deal with the brain, while although there is interesting things to very interesting things to discuss in the brain, but this is not the focus today. So this is the outline of the talk. So emotions are an old and common thing, and so of course it has been discussed for a long time. So we will start with a short historical and philosophical perspective. Then we will briefly discuss some psychological, some theoretical psychology, and very short things on neuroscience, because neuroscience could be another talk. There is a lot of research in there where mathematics can play a role. Third, I will introduce a mathematical model, a dynamical system, which relies on the electromagnetic waves analogy. So this idea, it's not from me. It is inspired by some philosophical works, but the mathematical model is new. Is totally new. And at the end, I will suggest a mathematical exercise which models the control of anger. All right, so let's go. There is not consensus on the definition of emotions, but I will say that emotions are a daily experimental living evidence, meaning that we all feel in a daily basis anger, joy, disgust, happiness, sadness, and so on and so forth. And this is the focus of the talk of today, the feeling of an emotion. I wanted to emphasize that the feeling of emotion is so universal that it is taught in a very early age. For kids, they at the age of 2, they start to learn how do they feel emotions. So there's a classical song for kids, but I'm not playing it right now. All right, see if you want more in-depth thoughts about emotions, I can recommend this. So for kids, Encyclopedia on Early Childhood Development. All right. So this was an introduction, right? Now I will briefly mention 3 points regarding uh, the historical and philosophical perspective about emotions. It will be ancient Greece, then we will go to Orient, and then I will mention the work of Sigmund Freud, the famous psychanalyst. All right, so emotions and their control were an essential point in the process of acquiring virtues in the ancient Greek philosophy. So Plato, Aristotle, Socrates, all emotions were central in the idea to acquire virtue and to act good, in fact. All right. So for example, for Plato, and there's subtleties in there. For example, so for Plato, uh, hunger is negative. Hunger is negative. However, there's subtlety because, according to Plato, one should not eliminate the anger totally. Instead, one should use it strategically and positively to control, for example, our greed or immoderate pleasures. For example, to develop the virtue of courage, or for justice, to defend our rights when it's legitimate. So again, I just give a flavor of that. There's a plenty of studies on ancient Greek out there. So here are some references. Okay, next I move on to some reference which is not very well known among Occidental mathematicians, but it's interesting to emphasize the universality of this topic of describing emotions. So I will just quickly mention a tale. So Rumi is a famous Persian poet, and so he has tales, but when he gives a tale, it's to teach a lesson. So I just briefly describe this one. So its name is The Tale of the Snake Catcher and the Frozen Snake. So what's the point? So there was a snake catcher who lived in Iraq, and so he went to the mountains to try to catch some snakes, and then he sees the head of a dragon. So he is terrified. He's filled with fear. But after he sees that in fact the dragon doesn't move. So in order to make some money and to acquire some notoriety, he decides to bring it to Baghdad. So the dragon was huge, but he strives, and he finally he brings the dragon to Baghdad. But well, the dragon was not dead. So when he arrived at Baghdad, he called all the people, come on, see, I killed the dragon. And so people come around to see what's going on. But with the sun shining, the dragon was just frozen, and then he wakes up, and so people are afraid. They run. A lot of people is killed, and the dragon swallowed. So it eats the snake catcher. So, well, the Rumi's tales are profound. I cannot give, of course, all the meanings of that. I will just emphasize one or 2 points. The dragon is very linked to emotions. In Rumi's perspective, he wanted to say that if there's no problem, sometimes emotions are not there's no stimuli for the emotion, so they don't manifest. But emotions can manifest if they are induced by some external events, and then you can lose the control, and it will be wrong for you for your behavior. Okay. So next, I will discuss the Freudian model. It's a functional, right? So functional means, so in physiology, the function is the role of a system. For example, a system in the body will do something. For example, the blood has to go in all the body, and its function is to give some nutrients to all the cells. And so the Freudian model is functional, so it doesn't aim to describe what's going on the brain, but what is driving us in a daily basis. So I will emphasize a few points about the Freudian model of the self. First, Freud introduces that in the mind, human mind, there is unconscious and conscious parts, meaning that there are processes that we are not aware of, but they are going on the mind and then can manifest after in our conscious, and they leads us to some behavior. So we will, for example, we will discuss anger, or sometimes you want to eat very badly something, and there is pulses that are pushing you to act in that way or this way, etc. And he introduces 3 entities in the mind. So it deals only with the psyche. There are now other models that are more involved. So he introduced the id. So the id is like an instinctual part of the mind that contains essentially libido or sexual and aggressive drives. And this will generate pulses and push us to do things that will optimize our pleasure. So the id, according to Freud, is driven by the principle of pleasure and will avoid the displeasure. Okay, so this id in the Freudian model is unconscious. Then you have the superego. Basically, it's the moral consciousness, and according to Freud, uh, it's educated by the social environment with rules, what your parents are teaching you, etc. And finally, the ego. So ego, um, in the US terminology, is the, so I will do some some French. In French, they will traduce le moi, but in US they say the ego, and the ego must balance all this and take decisions in interaction with the external real world. For example, I don't know, uh, you would like to, you are interested in the wife of your friend, but of course it's not uh, acceptable according to your principles, although nowadays somehow different, but the superego tell your id pushes to do that, but your superego tells you no, don't do that, and the ego must decide based on all this information, and I will say fluxes. All right. Uh, Again, so the Freudian is very famous. The Freudian theory. So it's the basis of the psychoanalytic theory, and it was very popular in at the beginning of the 90s. So here are some reference, and I put one in French, although you can find it in English also. All right. So of course, I'm telling you all that. It's because it will be interesting from a mathematical point of view. Okay, so then a few words about psychology and neuroscience. Um, so modern science has tried to study the emotional phenomena with they trying to give some proof of this phenomena. So I will describe a few things in psychology and in neuroscience. So first, let's discuss some psychology theories. So the famous theory is the discrete emotion theory, which generally includes disgust, fear, happiness, joy, and anger. And a fundamental paper on this is this one. What is this paper about? So these two authors performed a study. They went to Guinea and they tried to make questions to people there that were not um, uh, aware of our culture. So the point of this was to say that, well, these emotions do not rely on some culture. They are independent of culture. So to do that, they tried to find some populations that were not in contact with culture in Europe and United States. And so they performed some studies and they found that they were also able to recognize those emotions. So the conclusion of that was that these emotions are universal. They do not depend on some culture or things like that. Actually, so they try to give a proof of that, but it's kind of, again, a living experiment, because we all experiment kind of these emotions like anger or fear. Uh, Fear is fear. Of course, there is subtleties after that, but there is a common basis for all humans. Okay, then, of course, some people tried to go to study in a different way. And for example, try to find some variables that we can quantify. And typically, they studied two dimensions: the valence, so meaning that is the emotion positive or negative, and arousal. Arousal, it's the intensity. So I put that in bold because it will be important for our mathematical model. Okay, then I'm mentioning the affective events theory because this theory focuses more on the fact that there is events that occurs in life, particularly in work environments, and these are stimulus for emotions. And so in this model, the time plays an important role because events occur along the time. And in this setting, manifestations of emotions are a dynamical process. And for this story, that affects our efficiency at work. So that private companies can invest in this knowledge to improve the results. So it has a very pragmatic effect. Any questions so far? Okay.
No, it's okay.
Okay, thank you. Oh, I didn't start my video. Okay, let's discuss now neuroscience. So there's a lot of work on neuroscience. So there's a lot of work on trying to characterize what's going on in the brain with regard to emotions and behaviors. But I'm not discussing that point today. I just want to mention a few things. Is the facts that brought the role of the so-called limbic system for production and regulation of emotions. So in the 30s, Clever and Bussy, they took off the amygdala in monkeys. And then they noticed that the monkeys would have a strange behavior. In particular, they will not fear things. So, and after, there is a very well-known case. So SM is a woman, and this woman has a disease, and the consequences of this disease is that, again, her amygdala doesn't work. And so this woman doesn't feel fear. So you can put a snake in front of her, she will not feel fear. So it's problematic because then she can have reckless behavior. And so this case served as a basis of a bunch of articles in the neuroscience community to study more in depth the role of amygdala in fear and the neuronal processes that are involved in the manifestation of fear. But again, the brain, it's another piece of the story. Okay, I will say that is complementary to the approach that I am considering here. Okay, so I will now provide a mathematical model, which is a dynamical system, which relies on the analogy with electromagnetic waves. So a few preliminary remarks. So as I said, this is beyond the brain, meaning that we have common feelings that we can feel and identify, right? And what we want to propose here is a mathematical model able to describe these feelings, and a mathematical model which is more complete than previous works regarding the description of these feelings. But this model in some way is functional. And so the model will be a dynamical system because the feelings that we experiment is moving across time. So it makes this suitable for a dynamical system approach. And last thing, emotions do have an intensity. So yeah, there's a lot of examples, and sometimes with heavy consequences. People, for example, with anger, they do something that's not useful for them. They can, I don't know, with a very pulse of anger, extreme case are they kill somebody. They don't control themselves and they have a gun and they kill somebody. It's an extreme case, but it exists. And now we can come back to, for example, the discrete theory of emotions. You distinguish fear, anger, happiness, etc. So, meaning that emotions have a qualitative component. And if you want to set up a model, this model should be able to provide a good description of these distinct qualitative components. Then emotions mix up. You can, they mix up. They are not, they can occur at the same time. And they vary in intensity across time, and these things are moving, right? And all these characteristics are characteristic of electromagnetic waves. In particular, electromagnetic waves can be, for example, music or colors. You can describe them with their spectrum, and this looks like to be a good approach to describe emotions with a continuous spectrum of frequencies. So the frequency standing for the qualitative signature of emotions. And of course, electromagnetic waves are defined as the sum of waves with a unique frequency. And the analogy is to say that our psychic state is the sum of emotions or fluxes with different frequencies.
So we come now to the model. The model that we propose is an equation with a non-local component. So it's a dynamical system. It depends on time. Here, the psi describes the psychic state. It's an energy at time t and location x in the mind. And it depends on what. So here you take the derivative with respect to the time t, and it depends on what. So it depends on many things. And these many things, I call it a function. So the function will be applied at the psychic state at time t, but I take the integral all over the mind. So, for example, what is f aimed to contain, to take into account? External things that will interact within us, and then there is different parts of the mind. For example, the id in the Freudian model will manifest in our conscious state. There are more precise recent models, but I'm not going to discuss about that in this lecture. So yeah, that's it. So again, I have a dynamical system. Psi is a psychic state, and this is the derivative respect to the time. And this integral means that all the parts of the mind, the id, the superego, will act and manifest, interact, and with external events, and this will give my psychic state at the time t. And then the other remark is that a relevant decomposition of my psychic state is along these frequencies they have talked about, the anger, the fear, and much more. So in an analogous way of the Fourier transform, we make the hypothesis that it's relevant to make the decomposition of my psychic state across all a basis of emotions, cognitive states. So in particular, if one of these emotions take over all the others, then you have kind of a discrete emotion, a single emotion that arises, meaning that only one frequency is dominant. But of course, in general, all these frequencies, all these energies will sum up, will mix up to provide your psychic state at time t. All right, so now we move on to this mathematical exercise, which I call the control of anger. So there is a typical experience that has been described by a large number of persons. It's an experience of anger, and following a stimulus. This can be in a familiar environment, a work environment, so on and so forth. But, for example, behavior of a third person induces a strong pulse of anger. For example, some people do something that you don't understand, that you find very wrong, or the person should listen to you, but she doesn't want to listen. And so this causes a strong pulse of anger, and then at the beginning it's very diffuse, but then you start to feel it and it's like you explode. And for example, if you had an object in your hand, you just threw it on the floor or something like that. So it's a famous scene in Hollywood movies, I guess. All right. The point here is that it looks like that. So the anger starts, you start to feel the anger, and then a pulse occurs. And if it's out of a limit, you explode. You threw an object on the floor or something like that. Okay, so it looks like the energy that people feel in such a state resembles this motion. And what's that? This is a mathematical tool. It's just a sequence of Gaussians that are converging to the Dirac distribution. All right, so this is a classical Gaussian in R2. If you take the integral all over the domain R2, it equals 1. But if you take sigma going to 0, this is going to the delta function in some sense. So we're going to prove this theorem, but I will let it as an exercise and then I will correct it at the end. So I already said that, but yeah, so again, I repeat, this seems to us an interesting way to represent, to try to represent, to visualize the energy of anger, which is at the beginning hidden, it's unconscious, then you start to feel it, and then at some point it explodes and you lose control. So we can go a little bit further. So let's say that this is the energy of anger. So I denote it by E of X, Y, and T. And now sigma is a function of time. And I take it to be solution of this linear equation. So if you take alpha equals to 0, the solution is just an exponential which decays towards 0. With so A is a given positive number. And I have an alpha. The alpha is my control. Do I control my anger or not? All right, now sorry, some other things again. So my ES is the energy. So what's the problem now? I don't want to explode if I have anger, so I want to control the anger, right? So my ES is the energy of anger that I want at the end of the process. So I want that a given amount of energy of anger, which has not to be large. Okay, I want a normal energy of anger at the end of the window, capital T. My EM is the maximum energy acceptable for all time. So I don't want to exceed given energy, which represents the loss of control. All right, so now sigma S is defined by that. So you just replace X and Y by 0, and sigma, yes, and so sigma S is related to ES, like that. And the same for sigma M, it's related to EM. So what I want that the ES, I want ES to be smaller than E at time 0, meaning that I want that the final energy of anger to be smaller than the energy of anger at time 0, 0 being the time at which I recognize the anger. So I want to be ES, I want ES to be smaller than E0. And EM is greater than E0. And well, since I have an inverse, this gives this relationship for sigma, right? Okay, and this is the problem. It's a problem of control, a simple problem of control, but which is meaningful. I want to minimize my effort. So my alpha, the alpha is the energy that I put in control. So I want the minimum effort principle. This is a principle in nature. Everything tries to minimize energy. So I want to minimize the interval between the time I will provide the work. So I want to minimize the interval between 0 and capital T of my alpha. But I want that my sigma of capital T be greater than sigma S, meaning that my energy of anger at time T, I want it to be smaller than the ES. And for all T, I want that sigma T be greater than sigma M, meaning that the energy of anger is less than EM, which is the maximal energy acceptable. And there is a theorem. So you can prove that any function alpha satisfying this those conditions is a solution of my problem P. Then you have this proposition, which is kind of corollary of the previous theorem. You just look for simple functions that can satisfy the assumptions. So again, I let you prove that as an exercise, and then I will provide the solution.
So we're going to prove that the sequence of Gaussians converges to the Dirac as n goes to infinity. So let's recall that f sigma n equals that. All right. Okay, and assume that So the sigma, if sigma n goes to 0, when n goes to infinity, then what? Then my f sigma n converges to the Dirac in the sense of distribution. Okay, so we are going to prove that. We're going to prove this theorem. So how are we going to prove this theorem? So we are going to estimate the difference between f sigma n applied to phi minus my Dirac applied to phi, where phi is a function which I can derive as many times as I want. And it has a compact support. So meaning that my f sigma n converges to my Dirac in the sense of distribution is saying that this quantity goes to this one. For every fixed phi, we have this quantity which goes to this one. So I want to prove that this is going to 0. This is converging to 0. All right. So I can write it like that. Minus, no, sorry, this is phi of 0, so the origin in R2. Okay, but since this integral without the phi is 1, I can write it as the integral over R2 of f sigma n phi minus, I can just add this integral and here it's my phi. So I will write here 0, 0 in R2 just to be clear. I can write it like that, right? But then, okay, let's write it one more line. So I can put my f sigma n in front of the other terms and I get phi of xy minus phi of 0, 0 dx dy. So now I'm going to split this integral in two. That's what I'm going to do. I'm going to split this integral in two. I will first integrate on a ball centered at the origin f and with radius gamma n. So the quantity here doesn't change, the expression here, and plus, so this integral is on the wall domain R2. So if I integrate here on the ball, I have to integrate here on the complementary of the ball. So the complementary of the ball is that, and both are the same term. And what is my gamma n? So I choose my gamma n such that So here I'm assuming without loss of generality that, for example, my sigma n goes to 0 as fast as 1 over n. So such that the integral of we will see that we can do that. All right. Okay, and then when I do that, I can do the following estimates. Let's first deal with that. So now I will bound this quantity. So this is nothing but my Dirac flight 5. So now, so I don't want this to be 1 over n, but sorry, it's on the complementary here. So we have that. If we have that, I can bound this, the absolute value of that, by 1 over n times, and this term here, I can bound it by the maximum okay. So if my gamma n is such that we have this equality, then I can bound this term by that. Plus, now I'm dealing with this term, so this term, and with this quantity here. And so what? So now so now this quantity here, I can bound it by, so if this integral is 1 over n, when I integrate this quantity on the ball, I get 1 minus 1 over n, and this one I can bound it by, I just apply this theorem, so I can bound that by, I just take the derivative of phi, and here, since my distance between 0, 0 and xy is less than gamma n, I got that. Alright? So now, so this is going to 0, this is converging to 0, and we will show that this also is converging to 0. And so then the proof is complete. So just let's prove that we can do this thing. It's an interesting exercise, so let's do that. So to that is the same work as proving that the integral of the quotient is 1. So what I am going to do is compute the integral over the ball centered at 0, 0 and of radius gamma of my f sigma, which is So let's do that. I will need, so this is classical. I will set up this change of variable. So x equals r cos theta, y equals r sine theta. And then I have this Jacobian. I take the derivative of this quantity with respect to r, I get cos theta, and with respect to theta, I got that. Then sine theta and r cos theta. And then if I look at this quantity, it's just r. So now, when I apply this change of variables, I get that. It's the integral between 0 and gamma of the integral between 0 and 2 pi. I can put that here. And now I got this nice integral. But you see that this quantity does not depend on theta. So 2 pi will cancel this one. So I get 1 over sigma of, and then I must compute this indefinite integral, which is sigma. I forgot the r here. Here we have the r. And so we got that. Which means that finally I got, and it's a minus, right? So I got 1 minus exponential of minus sigma squared. Sorry, what is sigma? Right now, so I want that to be 1 over n. So this means that this has to be 1 minus 1 over n. So this leads to, so let's finish this stuff. This leads to then we obtain that, all right, meaning that my gamma n will be equal to, since I have assumed that my sigma n is going to 0 with the speed of 1 over n, this is going to 0. Of course, if sigma n will go slower, then I can choose this quantity such that I have to choose this quantity such that this one times this one equals to 0, goes to 0. All right, so yeah, we got this proof. Okay. So we are now going to prove the theorem 2 and proposition 1. So I'll first recall the problem that we are dealing with. So we want to minimize we want to find a function alpha which is positive and minimize this quantity, but under the constraints that so the constraints are that my sigma at the final time capital T is greater than my constant sigma s. So this stands for that the energy of anger at time capital T is back to a normal. Okay, I'm no more in the state of anger. And also I impose that for all t in the interval, the sigma t is greater than sigma capital M. So this stands for the fact that for all time I don't want to lose control, I don't want to be in a state that it's not acceptable. So sigma M refers to the maximum level of anger acceptable. All right. So now how the proof works. So let us recall that the sigma is solution of this simple ODE. My initial condition is that, and also I impose that the alpha at time 0 equals 0, meaning that I didn't start to control the anger at the beginning. All right. So once I have that, I just remark that I have an explicit solution for sigma. So we have that sigma equals sigma 0 exponential of minus a t plus the integral between 0 and t of alpha s ds. So now I just apply the logarithm and I put this quantity on the one side, and I take capital T. So I take t, small t equals capital T, and I apply the logarithm on both sides of the equation, and I get that the integral between 0 and t of alpha s ds equals log of sigma of t minus log sigma 0, and so sorry because I took the capital T, plus a t. All right, now I remark that I have this constraint and I want to minimize this quantity. So if I want to minimize this quantity, I just take the minimal value possible for sigma, which is sigma s. All right. So then if my alpha is such that this quantity equals log sigma s, this doesn't change, I got a solution. But also I have to, my function alpha has to satisfy this equation so in order to have that, I just say that this quantity must greater than sigma n, and I apply again the logarithm, and so I get this time that for all t, the integral between 0 and t of alpha s ts must be greater than so log of sigma m, and then it's the same, minus plus 80. And this is the theorem, all right? All right, so I repeat, the theorem 2 was saying that if I have a function alpha that satisfies this equality with, I replace here sigma of t by sigma s, and my function alpha satisfies this inequality, then it is a solution of my problem P, and I have explained what. Now for proposition 1, I'm just looking for a simple function alpha. I'm looking for the simplest function alpha that satisfies the constraints or the hypothesis of theorem 2. And in order to do that, I could try to have a constant alpha, but it's not possible because at time 0 I want that alpha 0 equals 0. So next I'm trying with alpha t equals ct, and then it's very simple computations. If I want to, if I want that the integral between 0 and capital T of alpha s ts to be equal with so I replace alpha of t by ct, and I get the expression in proposition 1. So right, this is c t squared divided by 2. So I get c equals all right, but then if I want this quantity to be positive, I have also to ensure that c t squared divided by 2 minus at plus ln sigma 0 minus log sigma m to be greater than 0. So I just compute the delta, and there is I compute the delta, then there's only two possibilities. Either delta is negative, this is the first expression condition in proposition 1, or delta is greater than 0, and then I must ensure that the first root of this polynomial to be greater than capital T to ensure that my function is remains non-negative. And that's it. So that's it, and so hopefully we can we can meet for the next lesson, which will be lecture 4. Goodbye.
Here, some pictures. So the first 2 rows are illustration of the energy of anger when I don't control it. So it explodes. It is close to the Dirac. Next, I apply a control. So it starts in a similar way. You see the first row in the, so the third row and the first row are analog. They resemble one with each other. But then, since I had some control, I put some control on it, I was able to diminish to the energy of anger and bring it to an acceptable level. All right, and here it's my E00 of t without control and with control. All right. So that's it. So the homework is the following. Try to prove the results that I gave in the talk. Well, since an interesting modeling, my evolution equation is a non-local, is with a non-local operator, it's meaningful that energies in the model can come from the unconscious and manifesting the conscious from the id, from the superego. So it's very relevant to have a non-local equation here. So I propose some lectures on this topic of non-local operators. So evolution equations with non-local operators. So here are some references. All right, so now I will provide the solutions of the problem.